Supposing you tie a string and you have two fixed ends. In that case, those two ends cannot move. So the string has to move between those fixed ends. Whenever a string is given such kind of a displacement, if any point is plucked in that particular string, the string is going to produce some oscillations, right? So those type of oscillations produce a standing wave. Why do we call it a standing wave? Because there is no net transfer of particle or energy. So that is what we call as a standing wave. Let's understand more about this. Moving on, we'll now try to understand about the standing waves. What basically do the standing waves actually imply? So when we talk about the standing waves is also known as a stationary wave, where there is no net transfer of energy or motion or particles motion taking place. So this is as a result of combination of two waves that are moving in opposite direction. They have the same amplitude, they have the same displacement, everything remaining the same. So when they move, one moving from here, other coming down like this. So as a result, if you sum it up, every time the particle will be always at the mean position. So that is when we call that it's a standing wave. This phenomena is the result of the interference. So the thing that we have just talked about, that is interference. So when the waves are superimposed, their energies are either going to be added together at the case of maximum amplitude, or they are going to cancel out. That is what is known as the case of interference, and that produces what is known as a standing wave. So standing waves, as you can see from this particular figure, you have particle, one wave going like this, the other wave going like this. So as a result, if you sum it up, the net motion is 0 at all points. Since the net motion is 0, that is what is result of the standing waves. Moving on from here, we need to understand about the nodes and antinodes, which we talked about before. So antinodes are the points here. So like basically these points, and nodes are basically these points. So if I have to just put it here, so if I just draw a line now, then nodes are these points where the displacement is maximum. Antinodes are those points like here and here. At the nodes the velocity is the maximum, at the antinodes the velocity is minimum, because the particle's trajectory is changing. Just after the antinode, it's going to start having some velocity. So on the path of the stationary wave, there are points where the amplitude is 0. These are known as nodes. They have the maximum velocity and so minimum amplitude. On the other hand, there are points where the amplitude is maximum. These are known as the antinodes. The distance between one node, or the distance between consecutive nodes and two consecutive antinodes, is going to be lambda by 2, because starting from one node to this particular node is going to be, so these are the two consecutive ones, and similarly these are the two consecutive nodes. So the distance between from here to here, that gives you lambda, and therefore between two consecutive nodes is equals to lambda by 2. Similarly between two consecutive antinodes is also equals to lambda by 2. Okay, let's move on and try to understand about the reflection of waves. So if you have a reflection taking place, so if you see like here, so here the wave is starting from here, it's getting reflected, means it's reaching here, it's getting reflected, and then its direction is changing. While a wave reflected from a free end, so if this end is completely free, it's just going to reverse back. Here in this case it is stopped, so there is a phase change actually taking place, and the phase change can be seen. So there is a phase change of 180 degree. If it is moving from, or if it is getting reflected from a free end, then there is not going to be any phase difference taking place. So depending upon how exactly the time period is different, that results into these types of waves. Okay, let's try to understand about the stationary waves in string. So if we take the case of, or let's say if you take the length of a string as L, which is stuck between 2 points, when this string is set into vibration, a transverse progressive wave begins to travel along the string. So here you can see that these are the nodes and antinodes are somewhere here. So the incident waves and the reflected waves interfere to produce a stationary transverse wave. So that is what is going to be result, in which the ends are always the nodes. The ends are going to be always here. So these are known as the nodes, and these points where the displacement is maximum, these are known as the antinodes.
The string vibrates in one loop in which the ends are the nodes that we have already saw, and the center is the antinode. So if you have one string, so you will have one particular antinode at the center. This mode of node vibration is going to be known as the fundamental node. So for instance, if you have this particular string, so there is going to be a vibration like this, there is going to be a vibration like this. So here this point and this point is, this basically point is the antinode, and here you have a node, here you have a node. So this is known as the fundamental frequency of the first harmonic. So the distance between consecutive nodes, as you see, is equals to lambda by 2, for the simple reason that the complete wave is not being completed, so you can only see half of it. So that's the reason you have a the distance between the two consecutive nodes is being equals to lambda by 2. So the length of the string, you can say, is equals to L equals to lambda by 2. So this results into what is known as the fundamental frequency of vibration. So according to the fundamental frequency, what you will have V equals to lambda 1 into F1. So that gives me, because from here lambda you can write it as twice of L. So if you substitute, you will get twice of L into F1. The same string under the same conditions may also vibrate in two loops, right, such that the center is also a node. So that can also be seen going further. So what do we have in this case? So for instance, you have something like this. This is one loop, this is another loop. This is known as the second harmonic or the first overtone. So this, if I say that this is the length, then this is also equals to lambda. In a similar way, if I talk about for the case when you have three loops, so you have this, this and this. So this is equals to the length, and this is going to be equals to thrice of lambda by 2, right? So these are the things that are there. So you will continue to have different harmonics depending upon how the waves are taking place, how the waves are moving. So a stress string, in addition to the fundamental mode, also vibrates with frequencies which are integral multiples of the fundamental frequencies. These integral multiple frequencies are known as the harmonics. This is very important. Now let's move on to understand the next thing. If the ratio of two frequencies is equals to 1, then they are said to be in unison, that is, they are moving together. If F1 by F2 is equals to 2, this is very, very important, then F1 is known as the upper octave of F2. If it's the other one, then F1 is known as the lower octave of F2. These are the things that you have to keep in mind always. There are some questions that sometimes you will be asked, that what is the upper octave, what is the lower octave. So if you take a ratio of two frequencies which are close together, means one is just a double of the other one, or the other one is half of the other. So you can use the lower octave or the upper octave to understand how exactly it varies. So hope you understood till this point. Stay tuned for more.
So as we saw, when you have a string that is stuck between two fixed ends, obviously its middle part is going to oscillate the most. Similarly, if you give an oscillation to the left part, there has to be an oscillation given to the right part, and that is going to be producing a standing wave. Why do we call it a standing wave? Because there is no net displacement being produced. But supposing there is some displacement, that is either of the two ends or both of the two ends are free, in that case that produces a displacement wave. So stay tuned for the displacement wave.